Thanks, Sumit, and thanks for the invitation. I've certainly learned a lot of things this week. And my initial title was, as Sumit said, somewhat more technical, but I kind of wanted to frame the kind of things I'm going to talk about at a slightly higher level, so I changed the title. The rest of the talks are of the talk is exactly as technical as it was before, but yeah, bear with me. So we have been talking about intelligence and learning and so on. And one aspect of intelligence that I want to focus on here is the interaction between a set of agents to achieve a certain outcome, right? So what I want to look at are certain problems where the intelligence is not contained in one agent figuring something out, but how these agents can interact in order to get their, satisfy their own utilities. And dually, the problem of understanding how responsibility for a particular outcome can be given back to each of the agents interacting together. So these are the two main problems that we shall talk about in this talk. How should agents interact to produce an outcome? And once you have an outcome, the backward view is for which portion of this outcome should each agent be held responsible. Okay? And for the moment, for the talk, we shall mostly try to construct a mathematical theory to answer these questions. And we shall leave aside certain questions about morality of actions and so on, maybe until the very end. And I have to start with a proviso that there will not be any large language models, and we will not train bees, we will not play with molecules. We will just talk about some theorems. Okay? Right. So let's understand this first aspect of the talk that I want to focus on. And this is about sequential decision-making with information asymmetry, which I think was my original title. Okay. So let's understand this notion of information asymmetry by an example that should be near and dear to many of the academics in the room, writing reference letters. So here's the situation. So I have graduate students, and I would like them to get good jobs. Okay? You, as a department chair, want to hire great new faculty. And in particular, you would like to hire my students, but you only want to hire the good ones. Okay? So your utility depends on you having hired a good student, and your utility is low if you hire a bad student. My utility is high if my student gets hired. Now, we both know that about 30% of my students are actually any good, right? So this is the prior, right? So 30% of the students in general, well, maybe some of you come from better universities, but let's say 30%. But the trouble is that I know which of these 30% students are good, right? Because I have worked with them and you haven't. So what you want me to do is you want me to write a reference letter for you, and you will base your decision based on this reference letter. So to look up my email address, you go to my web page. And my web page says the following, right? So I will paraphrase the math. The web page says that I'm going to lie to you occasionally. Okay? So if my student is good, my letter will say, yes, this student is very good. But if the student is bad, with some probability, I'm going to say, yes, this student is not so good, don't hire the student. But with the rest of the probability, I'm just going to lie to you and say, this student is super good, hire the student. And this is on my web page. The probabilities are there. The fact that I'm going to lie is there. And we both know that the prior is 30% of the students are good. So now you get my letter. You are a perfectly rational Bayesian being. You will figure out, given the signal, what is the probability that this student is good? And if the student, if your expected utility is greater than 0, you're going to hire the student. It turns out that if you run the numbers, then you're going to hire about 60% of my students. And this is after knowing that 30% of my students are good, and after knowing that I'm going to lie to you every once in a while. Okay? So this is the power of information asymmetry that we want to understand in this talk, okay? Or at least some aspect of it. So just to put the results in context, so what are the more classical models in which we look at this kind of sequential decision making? The very classic model is that of a Markov decision process. You have an agent that's interacting with the world. It observes the state of the world, and it takes an action based on this observation and gets a payoff. And the goal of this agent is to essentially find an optimal strategy such that if it interacts with the environment in this way, it optimizes its payoff. Okay? And Markov decision processes are very well studied. They're polynomial time, in order to find optimal policies and so on. Now, even in the one agent case, you can add partial information where you do not see the entire state of the world. You see some partial information about it, and you have to kind of base your action based on this partial information and your beliefs about the state of the world, and you get a payoff. And this model is called POMDP, partially observed Markov decision process. And what happens is that as soon as you have this partial observability, the complexity of the analysis goes up. So finite horizon cases are already p-space hard, and infinite horizon problems are actually undecidable. Right? And p-space hard, NP hard, these things are algorithm speak for saying that these are intractable problems. It's very unlikely you have an efficient algorithm. And you can now put in two agents that are both interacting with the world, and again, you can imagine that both of them have their own actions and both of them have their own utilities, and they interact repeatedly with the world. And this is something called a stochastic game. And again, the complexity of a stochastic game is essentially harder than polynomial time. For various simple versions, the best algorithms we know are in NP intersect ONP, but we do not know polynomial time algorithms. So in general, you see, we are looking at these kinds of interactions of various agents with the world, and classically, we know a lot about their algorithmic characteristics. So here's where we introduce this notion of information asymmetry. This actually comes from the economics literature from a very famous paper by Kamenika and Genskow, where they call this Bayesian persuasion. Okay, so just to recap this example that I showed you in the beginning, in the light of these classical models where you have a principal and an agent, and the asymmetry comes in the following form. The principal can look at the state of the world. The agent does not know the state of the world, and this is information asymmetry. But the principal does not have the power of taking an action based on its information. The principal has to rely on the agent to take an action that changes the world, right? That affects the world. So what the principal can do is signal to the agent about the state of the world. It can send some signal G about the state. And based on this signal, the agent can take an action, and then both of them get their payoffs. Okay? So the prior on the state of the world is known to both the principal and the agent, just as both of us knew that exactly 30% of my students are good. So the state of the world was the realization of a particular student, whether that student is good or bad, which is something that I observed, but you did not. And the signal was the reference letter that I sent to you. Okay? And your action was based, don't hire based on this letter. Now, one aspect in Bayesian persuasion is that the principal has this power of commitment. The principal can write down and commit to a particular strategy that says what signal will be sent based on an observation of the world. Yes?
So signal is a partial information about the state, or signal can also lie about the state?
Signal can lie about the state, right? The signal can be, I won't tell you anything, or I will tell you all the information, right? And the goal of what we're going to do is to find out a signaling strategy, right? So based on this, on the signal, the agent performs a Bayesian update, and then it takes an action that optimizes its own reward. But the principal's goal is, of course, to make sure that this action optimizes the principal's rewards. Okay? And the problem here is, how do we compute these optimal strategies? Yeah.
So how critical is the assumption that the prior is the same for both the principal?
At least in this model, it's kind of important, right? So yeah, or at least for the algorithms to work, it's important, right? Now, Bayesian persuasion has a dual problem that you may also know about, which is called mechanism design. So you can think of persuasion as a case where I observe the world, so I have sensors, but I do not have actuators. So I sense the world, and I must signal to an agent who can actuate based on my information, and then we both get rewards. Okay? The dual problem is mechanism design, where I don't have sensors, but I have actuators. So I want the agents to report to me the state of the world, and then based on that report, I will take an action. Right? So whatever we'll talk about in persuasion, there is a dual version in terms of mechanism design. Now, there are two simple cases that reduces this problem to the prior ones. So if our incentives are completely aligned, right, then my optimal signaling policy is that I should reveal all the information to you, right? Because whenever you do well, I do well as well. So any information that I can give to you about the state of the world, I should give to you. Similarly, if we are completely adversarial, right? So whatever you gain, I lose. My optimal policy should be to tell you nothing, right? Because any information I give you about the state of the world is to your advantage. But the interesting thing happens when we are interacting where we don't have a kind of zero-sum or adversarial setting, and yet our incentives may not match up, right? And the reference letters is one of these examples where our incentives are mismatched. So the reason why we started looking at this kind of games with asymmetric information is in the context of explanations in AI, right? So there's a lot of work, as you very well know, in trying to make sure that whatever models we are doing can be made interpretable or can produce explanations. And there's an implicit assumption there that, well, explanations are good, right? A model that produces explanations is actually better than one that doesn't. And I think one of our reasons for studying these things is to study this notion of explanations from a strategic perspective. Of all the possible explanations I can give to you about a phenomenon, I'm going to choose the particular explanation that is most beneficial to me. Right? So for example, there's this classic example of a bank loan and the bank providing an explanation of what you need to do in order to get a loan. And of all the possible things that you could do, invest in my bank might be an explanation that the bank might prefer than something else. And I think this notion of persuasion or mechanism design is putting this notion of strategic explanation on a more mathematical basis. I will go through very briefly of how the underlying algorithms work. The first point is that, well, what is the signaling strategy? That goes to Sumit's question. So in general, a signaling strategy looks at the state of the world and gives you some distribution on a space of signals. Okay? And the space of signals is completely unspecified at this point. It's some arbitrary set. But you can use some well-known results in game theory to kind of reduce this to just the actions of the agent. So for example, this is a signaling strategy because you see it looks at the state of the world, and then it produces some distribution over the signal. The signal here is good or bad, right? And the signal kind of corresponds to the state of the world here. And well, upon receiving this signal, the agent essentially gets a posterior of the distribution of the state of the world by using Bayes' theorem. And in this particular case, if you work it out, it's 0.5 something. And then the agent, here I call it the buyer, essentially runs a maximization routine where they maximize over their actions of the expected utility of the agent given this posterior probability distribution. Okay? And the goal of this one-shot Bayesian persuasion is that, well, I want to, the principal is trying to optimize their policy over this over the signaling space such that they optimize their expected reward. Okay? The principal's reward when the optimal action is picked by the agent based on the information that they have received. So there is a famous paper in economics saying one quarter of the GDP is persuasion. It sounds very attractive until you actually read the paper and where you realize that the authors have just made up these numbers, right? They've said, well, let's look at the different professions there are in society. Priest, 100% persuasion. A teacher, 70% persuasion, and so on. But one cannot argue, I guess, with the central premise that a lot of economic activity that we do is really based on this kind of interaction where there is asymmetric information between the sellers and the buyers or between the principals and the agents. Okay, so I talked about information asymmetry and the one-shot version of it. What we actually studied was a sequential decision-making version of this. So in this sequential decision-making version, you essentially have this kind of one-shot as we had before, but the game continues over time, right? So the action of the agent influences the state of the world, and the game keeps continuing for some t steps. T can be infinite if you're thinking about the infinite horizon problem. Okay? And there is some hindsight where both the principal and the agent get to see what the state was in the previous step and so on. So why do we want to study this kind of sequential persuasion problem? Well, it turns out that many of these things, like in app design and so on, there is again this kind of a repeated game over time between the app builder and the users of the app, where the incentives of the app builder and the users may be somewhat misaligned. Okay? So for example, the app builder may have real-time traffic information, and they may want to route the traffic in certain ways. But for an individual agent, what they want to do is go from point A to point B in the shortest possible time, right? So even if it helps the app builder, this incentive may not be aligned with the user of the app. Okay? And just to look at a very simple example of how this kind of sequential game goes on and what is the role of this information asymmetry, we can think of a very simple setting where we have an agent that wants to go from S0 to S3, S0 to either S1 or S3. And there are some rewards that are along the edges of the graph. And let's say that the agent's goal is to maximize the sum of rewards with some discounting. Okay? So if you work out what the agent can do, they can either go up there, and they would get a reward of 0.5, and they can go down there, and they would get a reward of 1. Okay? So without any more information, the agent should just take the bottom row and get a reward of 1. Now imagine there's a principal who, for whatever reason, wants the game to end up in the state S3. Now, without any information advantage, the principal cannot influence the agent's behavior, right? The agent is going to be maximizing, it would take the bottom path. But you can think of, in this particular very simple example, how information asymmetry can play a role. Imagine that there is some external parameter that's sampled at S0, whose realization is known by the principal, but not by the agent. Okay? And the prior of this parameter is known to both principal and agent. And in this case, let's say that the state of the world when you're in S0 can be either A or B. And with probability half, it's going to be A. And with probability half, it's going to be B. Okay? But whether it's A or whether it's B is known only to the principal. Now imagine that the reward that the agent gets, if the state of the world is A, is, if it goes along this road, then if the state of the world is A, then the agent gets a -10. But if it's B, then it gets a +10. And similarly for the other one. Okay? Then to the agent, without any more information, the expected value for picking one of these things is just 0, right? Because, well, I don't know if it's A or B. If it's A, I get a -10. If it's B, I get a +10. My expected reward is 0. And this is essentially what we modeled, and similarly for B, right? And this is what we modeled when we said that both of these edges have an expected weight of 0, expected reward of 0. But of course, once the principal can signal this information, then suddenly you can influence the way the agent will behave, because what the principal can do is essentially give a signal that says whether the state of the world is A or B. Okay? And with this additional information, suddenly the structure of the graph can change. The structure of the graph now becomes something like this, where the agent has a lot more information based on the signal, and therefore can pick the appropriate path. Right? If the state of the world is A, then the path will be that one, and if the state of the world is B, then the path will be the bottom one. But in both of these cases, the game ends up in the state S3. Okay? So this is essentially a small example to show that how this game goes on in a repeated setting and what is the value of this additional information. Okay? So what we were interested in is to understand the algorithmic basis for these kinds of problems. Okay? So imagine that we are in a setting where the possible states of the world are finite, and we are in a setting where the possible actions set is also finite. What can we do algorithmically? Now, it turns out that if you just have a one-shot Bayesian persuasion setting, then this one-shot problem can be reduced to linear programming, so it's essentially can be solved in polynomial time. Okay? Now, when we looked at the sequential setting, we started looking at how agents behave. And we looked at certain different classes of agents. The far-sighted agents are the agents that are most powerful, right? So this is an agent that is playing with you over time, and their goal is to optimize the long-run sum of the discounted rewards. Okay? But we also looked at a class of agents called myopic. And you can think of a myopic agent as a game with a myopic agent as follows, right? So you have a principal that's long-lived, that's playing the game for the entire duration. But you can imagine that at each step, a new agent comes, and the goal of this agent is only to optimize their local reward. They don't care about the future. What they care about is what happens to me now, right? So I want to pick an action that optimizes my reward in this step. And once that happens, this agent disappears and a new agent comes in. And the reason why we wanted to look at these myopic agents is that in this kind of an app setting, the app builder is someone who is there for a long time, but the app users are interacting for short times with this app. So having a myopic view of these agents is a reasonable approximation to the way many users would behave. Okay? And then we looked at something called advice myopic that kind of sits in the middle. Maybe it's not so important for this talk. And the main results that we have is the following. If you have a far-sighted adversary, then computing the optimal signaling policy is hard. It's NP hard even to approximate. But if you are only concerned with myopic agents, then actually you can solve this problem, again, by a reduction to linear programming, so there is a polynomial time algorithm. Okay? And more recently, we also have results in the finite horizon setting where all of these problems turn out to be polynomial time. And we also have results about learning that says, well, there is a low-regret learning algorithm in this setting of sequential persuasion. So this is kind of I will stop here talking about this particular aspect of the work where we have explanations that can be used strategically by the agents. And this might be a good place to stop for questions if you have any about the first part of the talk. Yeah.
If I'm understanding correctly, there isn't a sense in which the agent can realize, oh, this communicator lied to me, I should therefore no longer trust their signals. Is that the case?
Oh, yeah. So for a far-sighted agent, because they know the prior, because they see the signal, so they can pretty much figure out that, well, this signal was not, this signal is a lie, right? And it should be built into the way it constructs its strategy, right? So you see, they know, because there is commitment, they know what is the signaling policy that will be used, right? So they know a lot of information, including the fact that the principal may be lying to them at certain points.
So is there a variant in which there isn't the commitment part, so the agent can't know, like a priori, whether or not they might be lied to?
Yeah. So in general, you can look at stochastic games. So those would be the general class of stochastic games with asymmetric information and no commitment. And there we have certain characterizations of the solution, but we do not have any algorithms. Mostly because these characterizations say that, well, the solution is a fixed point over the set of convex functions, and I don't know algorithmically how to implement it. Yes.
Can you say a few words about why that particular problem was going to be hard?
Let's take it offline. I mean, it's one of those things where you kind of look at the problem, you realize that, well, I can encode some, I don't know, I think in this case it was the graph click problem into a game of this kind. I don't think there was any deep insight. It's just you do a reduction. Yes.
On similar lines, you mentioned earlier, and I guess it was not concerning these problems, the ones you were talking about before, that some situations with an infinite horizon is actually uncomputable.
Yes. So if you have partial observer, POM-DPs, and if you have certain decision problems on POM-DPs where you're trying to optimize the infinite horizon reward, these problems are actually undecidable.
So that means that this is actually, in a certain sense, easier than others.
Yes, yes. So that was the surprise, right? That if you naively add if you naively add partial information to an MDP, you expect that the complexity can be very bad. But what is surprising here is that there is adversarial interaction as well as partial information. But in this particular setting, the problems are still easy.
But intuitively, why? Because the adversary, you would think, could make life harder for you than by just having a noisy channel. But I'm still getting noisy information, but it's designed to screw me up.
Yes. So the intuition here is the following, right? So first of all, there is this commitment. And the other is that after some reductions, you can show that the optimal signaling policy is something that asks the agent to play something that's incentive compatible, right? So the signal is essentially what action the agent should be playing. And the agent can essentially check that if they play this action, then their expected payoff is at least as good as if they switch to a different action, right?
I see. So the adversary has to presume that the agent will be doing that much. So
the adversary so the principal in their calculation can figure out an incentive compatible signal.
So it's almost like the adversary is providing a certificate in the sense of an NP proof. Yeah. And it's actually more like an interactive proof. Okay, anyway, very interesting. Thank you.
Right. So at this point, let's go to the second part of the talk. And this part, in some sense, is perhaps less mathematical and more philosophical, where our goal is to understand how to ascribe responsibility in situations where multiple agents interact in order to provide a certain outcome. And again, instead of going through some formalisms, we'll just go through a few examples, right? So the first example is that, well, I'm traveling, and I ask you to water the plants in my office while I'm gone. You forget to do it, and the plants die, right? So who is responsible? I won't give you the answers right away, but these are things you can think about if you get bored with the rest of the slides. Right? So the next one is a very classical example in the theory of causality. So Billy and Susie throw rocks at the same time at a bottle. Billy's throw hits the bottle and it breaks it. Okay? But Billy's throw just reaches the bottle and hits the bottle a moment before Susie's rock would have hit the bottle. Right? So who is responsible for breaking the bottle? And the third one is one of my favorite examples. There are two assassins who are trying to kill somebody in the desert. So assassin 1 poisons the water bottle, right? But assassin 2 did not know this, did not know that assassin 1 existed, right? So they just decided to poke a hole in the water bottle so that the water runs out. And this person in the desert dies out of thirst. So who is responsible, right? or to what extent are they responsible? And you can imagine that, well, assassin 2 might say that, well, I threw the water away because it was poisoned, so certainly I should not be held responsible. And assassin 1 would say, well, my poison was never used, right? It went away, so I am not responsible. Okay? So here the question is, before you want to start thinking about these kinds of issues formally, what is the right definition? What is the right framework to think about responsibility attribution? And this is what we studied, right? So we essentially came up with 3 conditions in this way of responsibility attribution. The first is agency, the second is causal relevance, and the third is the ability to act otherwise. Okay? Now, agency is maybe the most philosophical. What you want to do is you want to have a model where these agents are aware of the decision situation, they're aware of the things that they can do, the other agents, and the possible outcome, right? And we also assume that these agents are able to plan and act intentionally. So if you think about this water bottle example, this plant example in my office, well, I do not want to hold, let's say, Brad Pitt responsible, because Brad Pitt does not even know that I am traveling and there is a plant in my office and so on. Even though had Brad Pitt broken into my office and watered the plants would not have died, right? So the other thing is that, well, if you have a baby, usually under all sort of legal frameworks, babies cannot be held accountable because they do not have agency, right? So they are not aware of the situation. While one can go into sort of more deep philosophical aspects here, our goal is that we will have a model where we will explicitly say, here are the agents who are within the purview of the model, here are the actions they can do, and here are the outcomes based on the collective actions of all these interactions. Okay, so this is just to set the stage that we will have a model. I'll come to causal relevance in a bit. The third part is, well, in order to be held responsible, the agents should really have the presence of alternative actions that could have provided a different outcome. Okay? So this is, again, a very sort of classic philosophical thing, right? So, and this is an example that illustrates why you need this ability to act otherwise. So, in a firing squad, usually, there are the 10 marksmen who have rifles, and only one of them has a live bullet. And they do not know who has a live bullet. They all shoot. The person dies, but usually this is done so that nobody has to live with the guilt of being the actual person who does the killing. Now, in general, this is done to kind of absolve responsibility to one particular person. And the point here is that there is no other action, right? In our model, you are a marksman, you're given a rifle, and you shoot, right? And your information set is that you do not know if your rifle has a bullet or does not have the bullet. So because we are restricting everything into our model, we are saying that the only action available is that you shoot. Because otherwise you get into these philosophical quandaries. What if one of them decided not to shoot at all, right? Because, again, we are thinking about a model, we will say, well, those things cannot happen. So essentially, the first and the third just set up the stage for a formal model where you have agents, each agent has an action, and based on these actions, there are various outcomes. Then the more interesting point from the analysis perspective is this causal relevance. So if the action, if the agent takes an action, then this action, there should be an action link between this action and the eventual outcome. And one way of formalizing this is through counterfactuals, right? So A is a cause of B. If had A not occurred, B would not have occurred either. Okay? Yes?
So is this framework only applicable to humans, or is this?
In general, right? I mean, there could be autonomous agents that are taking various actions. But hold your question for a while, right? I mean, so far there is nothing about humans. It's just that the agency is usually ascribed to humans, but since we are in this model-based framework, it doesn't really matter, right? It's just, here are the available actions to an agent, right? So what we do is that because we have set up this model, we can again use games of all these various kinds that I showed you before, stochastic games, asymmetric information, and whatnot. And I can study this notion of causal relevance and responsibility in this world. And once you have a game, you can define a strategy. A strategy is a plan for each player, how to pick the actions given the history of the game. And then, in particular, if we think of a particular outcome E, in this case, the outcome is either green or red. But for an outcome E, I can say, well, if everybody has picked their strategies, what you have is a path that tells you what happened in the game. And that path is an E play if the outcome is E, and if it's not an E play if the outcome is not E. Okay? And then you can define sort of two notions of responsibility. There's a forward notion where you say that a coalition of players is forward responsible if they have a strategy such that no matter how the rest of the players decide how to play, the outcome is not E. Okay? And there's a backward version of responsibility where you're given a particular play, and you're saying who is responsible. And the backward responsibility is that a coalition is backward responsible if they have some joint strategy such that there is some node along this play such that if they change their strategy from that node, then the outcome would not be an E play. Okay? So I'm given a particular scenario. This is what actually happened. You look at it and say, well, if this coalition decided to do something along some ancestor in this path, then the outcome would not have been E. Okay? And I think it's a very interesting result that if you have a game of perfect recall, and perfect recall just says that as you play the game, you remember everything that has happened in the past, right? So in a very general notion, in a very general class of games, if a coalition is forward responsible for E, then they're strategically backward responsible along all the E plays, and conversely, right? So philosophically, forward responsibility and backward responsibility have been studied as sort of distinct notions. And what we can show is that if your game has perfect recall, then these two notions coincide, under all the assumptions that I made before in terms of the model of interactions that we have. Okay. Now, what is very nice is that using this, we can go back and analyze all these examples that I gave before. And I don't want to do this analysis. Perhaps you can think about it by yourself about who should be responsible in each of these cases. But you can actually go somewhat further and also ascribe individual responsibility, right? So far the responsibility was at the level of the coalition, but philosophically responsibility lies with the individual. And the simplest way of ascribing this individual responsibility is through Shapley values, right? So again, you may have seen the use of Shapley values in explainable AI, but it's a very general concept that essentially tells you in a cooperative game how rewards should be allocated to people. And essentially, you can set up the right cooperative game and figure out that the Shapley value is exactly the extent to which individuals can be held responsible. And all of this is essentially modulo the model and all these assumptions that we have made. Okay? So just as an example, in the Billy and Susie case, you can show that they're both equally responsible, even though one of them, the actual causality was that Billy's rock hit the bottle. And the two assassins case as well, both of them are equally responsible. But here's a homework problem. This is a somewhat more complicated version of what we have seen before. Here you have, three people need immediate aid. There are 4 bystanders that show up in that order. And each bystander can help one of the victims. And we assume that they help a new victim if someone's already been helped. And let's consider the event where one of the victim dies, or at least one victim dies. So suppose that you are in a situation and 1 and 3 helped, and 2 and 4 did not help. So how should this responsibility be allocated? And the other case is that suppose that 4 would have helped if 3 had helped, but 3 did not help, but 2 and 3 did not help. And then how should responsibility be allocated in this case? So we can talk about this over coffee or lunch later.
question.
Yes.
In cooperative game theory, there are many solution concepts for how to divide out besides the Shapley value.
Yeah, exactly. So you could use roughly any one of them. So we use the Shapley value because there's a nice generalization if you have a continuum of players, right? So there's a generalization of the Shapley value that you can do there.
That's not true for other.
It gets very weird because sometimes, for example, certain solution concepts may not exist, right? So you want a solution concept that always exists. Okay, so I think I'm running out of time. Okay, I do. Okay, good. So at this point, we have a reasonable mathematical theory, and the question is, are we done? And all of you have been in enough talks to know that any question of this sort has an answer that is no. And the reason is that, well, human decision-making may not always be reducible to this kind of reward structures where you have some kind of utilities, rewards that have a lot of structure that's assumed implicitly. So whenever we think about games or optimizations or learning and so on, one of the basic assumptions that we make is that we have a reward structure where the rewards come from some ordered field, right? So you can compare rewards. This comparison operator is transitive. We can do addition of rewards. We can do linear optimization on rewards, and so on. And the other assumption that we made is that when you look at a coalition, essentially the way you aggregate the utility of a coalition is by summing up the utilities of the individuals. And the reason why you kind of do this aggregation is because of a result from utility theory that says that, well, if your utility function satisfies some basic assumptions, which include this kind of transitivity of utilities and so on, and if you believe in some very natural assumptions, then this is really the only, full aggregation is the only way of combining individual utilities into group utilities. Okay? So you can, the best you can do is take the weighted sum of utilities, and that is the utility of a group. Now, this may not always be the right approach. And this is an example that, again, many of you have seen before, right? So this is a variant of the trolley problem. Well, you are a surgeon, you have 5 patients who need organ transplants. This is deliberately written as a prompt to an LLM, if you wish. But essentially, this is the problem where you can kill 1 person in order to save 5, right? And there's a question in moral philosophy, well, do you do nothing, in which case these 5 patients will die? Or do you kill this young man and distribute his organs in order to get 5 people to let 5 people live? In any sort of utility aggregating situation, well, you would probably kill the person and distribute the organs because 5 people live as opposed to 1, right? But of course, from a moral philosophy standpoint, this is perhaps not the right thing to do. And if, like me, you live in Germany, this is constitutionally not the right thing to do, right? So there is a German constitutional court ruling that says, in a situation like this, you cannot kill 1 person for the good of the many, because it goes back to Kant. You cannot use humans as an end, as a means to some other end. And the German constitution actually encodes this and says, there was a very famous case where if an aeroplane has been hijacked by terrorists and it's going to crash into a stadium, and the stadium is full of people, is the government allowed to shoot down this plane, even though there are other innocent people on the plane? And this ruling said, no, you cannot do this, because Kant. Well, the ruling said you can't do this. Okay. And yes, please. Yes.
What about the famous example when Churchill knew that they were going to bomb Coventry and didn't want to reveal that they had broken the codes?
Yes, and
to save lives. I mean, does the Constitution protect that? Only
These are constitutions of different countries. We cannot get into
I
this.
know that.
Only because you brought it up. I know it's not really,
Yeah, we were on the other side of that decision.
I understand.
Okay. And you can see there are other similar problems with full aggregation, right? So suppose that you can save some person from death if you allow a large number of people to have headaches, right? Some minor inconvenience. So usually you will say, well, a minor inconvenience, no matter how many people have it, is not comparable to a death, right? But you can ask a similar question. What about it's a huge number of people who are paralyzed and live very bad lives, right? Would you still consider this? And these are not answers that one can give purely numerically. Right? And you can have a probabilistic version of this case, right? So you have a headache, and you can treat your headache, but you know that there is a very small probability that someone will die, right? Let's say 1 by 1 million probability. So do you take care of your headache even if someone can die with a very small probability? And the answer is yes, because I will drive to the drugstore, and along the way, maybe I have an accident and somebody dies, and there's a 1 in a million chance of that happening. But I will still drive, right? So many of these questions are not so clear. So in the world of philosophy, there's a lot of theory that says, well, you can come up with a theory that's not fully utilitarian, that does not always aggregate, but it partially aggregates things, right? Certain things are comparable, certain things are not comparable. And you can provide a philosophy that says, well, this may be a good way of doing aggregation when you're thinking of moral issues and utilities. Yes?
Well, the standard way of going after this is revealed preferences. That, for example, in the US, the human life is valued at, it varies, it's changing in time, but something like $5 megabucks. And that's because that's the amount that somebody values their own life. There's all kinds of revealed preferences that say you don't value yourself more than about 5 million or some such number, and bing, bang, dum, plug that in, and there's nothing incommensurable about dying versus some kind of quadriplegia or something. Just go to reveal preferences. Nobody gives infinite value to anything, full stop.
One might argue if that is the right moral setup to think about human lives, right? So, but my point here is much simpler, right? So I guess, yes, if there is a way of assigning a number to human lives that everybody agrees upon, not as a statistic, but also with your own life, right? I mean,
That's
if today...
Reveal preferences, yeah. This is your own life. There are many things that you do. It's very, very simple to set up. It's like prediction.
Would Elon
models.
Musk agree that his life is worth 5 million?
No, obviously it varies from one person to another.
Right.
But nonetheless, there are these averages. Everything.
So the point is that in an interaction, why will I not get into this thing about, name the largest number, right? So imagine that in an interaction, one of us will be better off. And the person who will be better off is the one who places a higher value on their life. This game does not have a value.
It's a practical issue. Every single government on planet Earth has to do this. They have to value individual human lives. Yeah. Well, that doesn't matter. The German government does it. There are many things the German government does where they do not put in infinite value to a particular human life.
Except...
Doesn't matter what that says.
Well, I'm giving you a very specific game situation where the government can decide to shoot down a plane or not. And revealed preference would have said yes, but the court says no.
There's what you're pointing out, is that the German government is not fully consistent. People in charge there should read their real preferences literature. But the actual government behaves in such a way in many other situations. Every single day, they're right now deciding how much money do I give to Ukraine. There are a lot of lives that are associated with these decisions, and none of them are given infinite value.
I agree. And all of these debates are exactly why I'm saying that a naive way of going to math is perhaps not the right thing to do, right? So just because people ascribe these numbers does not mean that we can completely remove the sort of ethical parts that go into these kinds of game models. We can have these discussions, and maybe at the end we decide that yes, assigning numbers is the right thing to do. But to me, what I'm saying is that there is a modeling issue here, right? Before I can start doing the math, I have to go through these issues and make sure that the modeling assumptions that I'm making make sense. Right? And I agree that you are saying that, well, these modeling assumptions make sense because revealed preference is all of these issues can be given specific numbers, right? Right. So, and what I wanted to show is that if you do not have transitivity in these kinds of reward functions, you can get into contradictions. And but let me skip this particular example and get to the punchline, right? So essentially, what I'm getting at is that human reasoning, especially about moral responsibility and moral behaviors, is not always reducible to aggregate behavior. But this brings us to a contradiction from the mathematical perspective, right? So what we don't know is how to set up an ordered field from which we can get these numbers. Now, you can say, well, why not use ordinals, right? Because if you know about ordinals and transfinite numbers, you can say that, well, this number is infinitesimally smaller than that other number, right? And therefore, I can model these kinds of preferences that you have that says that, well, a human life is worth infinitely more, let's say, than a headache. The trouble is that if you just have ordinals, this is not enough because, as I said, you need an ordered field. You need to be able to do optimization and so on. And so at this point, you can go full math nerd and say, well, go to a very large field, maybe the field of surreal numbers, which has these infinitesimals and also allows you disordered fields and all these other nice things that you want to do. So how many of you know how surreal fields work and whether linear programming works in surreal fields? And yet, all of us are doing all these decisions, right, in real life. So this cannot be the way humans, when interacting, are thinking about their expectation maximizations. So this is roughly where I will stop, right? So I think what we started with is some mathematical notion to understand strategic interactions and later on to understand responsibility attribution. But when we start talking about responsibility attribution, we get into situations where the math works but is perhaps not the right framework to do. And what that framework is, I do not know. Let me stop here and take your questions. Thank you for your attention.